Okay, so over here, I've got a couple of equations. I haven't set them all up. We ran out of time, and I wouldn't have gone to the extent of setting up all 11 equations, although it would have been fairly easy to do. It really wouldn't have taken that long. I'll leave you to that. I only set up an equation for one branch point and one loop, and we'll explain how that goes. This stuff here is from a different class. I had to, had some technical glitches and ran out of boards, so I had to borrow a piece of blank board here. Okay, so I let people decide which branch point they wanted to use, and they wanted to use D. Okay, that's a good one. Okay, in D, what currents do you have? Now, you might have, if you enlarge your picture a little bit, you might actually be able to read these. So maybe I better clarify them. This is I7, goes this way. This is I8. I had to write that pretty small. And I've got the head of the arrow going this way, so I've assumed I7 goes this way, I8 goes this way, and I have an I11 here. Okay. 3 different currents, some coming in to some coming out of this branch point. Again, it really doesn't matter if I've got them in the right direction, because when I solve my equations, if like I8 really should be going that way, my equations will tell me. I'll get a negative for I8 telling me I better reverse that arrow. Okay, so all I got to do to set up my equation for D is say, okay, let's see, I've got I8 coming in. So when I do the sum of the currents in, I8 is going to be positive. I7 and I11 are going out. They're going to be negative. So I'm going to have I8 minus I7 minus I11. And the sum of those three, that's all, those three are all that flows into this point, or into and out of this point. They have to add up to 0, because charge can't accumulate at this point. So here's my equation. Now that was really easy. And it's equally easy to write the equations for the other branch points. Okay, now let's do an equation for a loop. And people say, okay, let's use loop 1. Well, you can probably see I've got this loop labeled 1. So we're going to do this loop. Now, if I go counterclockwise around this loop, okay, I'm going to encounter V3, and V3 goes from positive to negative, and that's a voltage drop. Now, I've stated this condition here is saying that the voltage drop around any loop is 0. Now, there's a reason we talk about voltage drop. Voltage drops when a current goes through a resistor. So we don't have to do any hard thinking about in what direction the voltage drops when we see a resistor. And it's equally easy to figure out if the voltage drops as we go in a certain direction through a source. If we go through V3 in the direction, counterclockwise direction, we're going to go through it this way. We're going to go through from positive to negative. The voltage will drop. That means the voltage drop is V3. Okay, so we have voltage drop V3. And let's talk about V1 here. We got V1. Well, here we're going from negative to positive. We're going counterclockwise, so we've got to go this way. So the voltage goes up, which means it doesn't drop. It does just the opposite. Well, that means the voltage drop is negative. So we're going to have a negative V1. Then we have this resistor, and what current do we have going through this resistor? Well, I1. I1 works from this branch point to this branch point. Now at every branch point, all your currents change their labels. Okay, so when we come out of this branch point, we've got I2, which goes around this way, and I3 that goes this way, and so forth. We don't worry about those because none of those currents, this one isn't even in the loop. This one is for a short time, but it doesn't go through a resistor, so there's no voltage drop. But there is a voltage drop here. Now, since I1 is going this way through R5, the voltage drops in this direction. But we're going around the loop counterclockwise, so the voltage drop is actually going to have to be expressed as a negative. So we have negative I1 times R5. Well, there it is. Those are the 3 voltage drops that we encounter as we go counterclockwise around this loop. Okay. Now, somebody said, well, okay, And I told people, okay, you're going to get 6 equations. Because you've got 6 branch points, you're going to get 6 equations for branch points. They're going to be very similar to this one, but with different currents and different signs. And you have 5 loops. So you're going to get 5 equations like this. Now, how many unknowns do you have? Well, we assume you know the voltages of the sources, and the only unknowns then are our 11 currents, and there are 11 currents. If you set up one, you know, for every set up the currents, okay? I've explained that. And I said, wait a minute, these 2 equations then wouldn't be compatible. Excuse me. Because the units are different. The units of current are different than the units of voltage. Oh, this stuff just chokes me up. Well, yeah. That's true. That's a good thing, and I'm glad that was brought up. Well, that's easy to remedy. Just divide by the resistance, and of course then you're just left with current here, and voltage divided by resistance is a current. So now you have everything in current. So you might use this in the equation instead of this. There are other ways you can reconcile that, but that's probably the easiest. So you're going to get 11 equations and 11 unknowns. And the unknowns are going to be I1, I2, I3, up through I11. Well, look at this equation. Only 3 of those variables have non-zero coefficients. So you're going to have a lot of zeros in that equation. And really what you're going to do is you're probably going to set up this system of equations as a matrix equation and do a matrix reduction. This is by far the most efficient way to solve these systems. And even for an 11 by 11 system, since in this system I don't think there's any loop or branch where you have more than 3 elements, there might be one with 4, I'm going blind, but most of your coefficients are going to be zeros. So you're going to have a matrix with a bunch of zeros, some non-zeros. It's going to turn out that that matrix is very easy to reduce to the identity. So you augment that matrix and so forth, and you solve your equations. And you find I1 through I11 in terms of V1, V2, and V3. And that's actually, you can actually do that by hand. You can do that row reduction if you're any good with row reduction in 10 minutes. Ultimately, of course, if you have a much more complex network, or even if you have an 11 by 11, you've got to feed it into your software. You're going to do an inverse matrix or something, and just solve it that way. Okay.